Bismillahirrahmanirrahim. Hi students, and now let's complete the continuous random variables and their properties. This is part C of continuous random variables and the properties. In the last lectures, we finished the definition of continuous random variables and the probability density function and the cumulative distribution function. Now let's begin with the expectation and the variance. For continuous random variable y, for example, with the PDF defined by small f for the random variable y of y, the mathematical expectation, or it's defined to be the mean or the expected value or the average of this random variable, is denoted by capital expected value of capital Y. And it's defined to be integration from the lower limit to the upper limit y itself times f of y dy. The upper limit and the lower limit in general, it's from negative infinity to infinity y f of y dy. If you remember, for the case of discrete random variables, it was the same. The expected value of y, it was the sum, okay, over all possible values of this variable, beginning from lower limit to the upper limit, and inside the summation we will put y itself times the probability of y. Okay, here instead of the sum we will use the integration. Why? Because we have infinite number of values or uncountable number of values that the random variable can take. If y is a continuous random variable, then for any real valued function, for any function of this random variable, for example g of y, the expected value of the function g of y, which is a function of the random variable itself. For example, the expected value of y squared, the expected value of ln y, the expected value of 1 over y, the expected value of y cubed plus y squared negative 2, for example. Okay? But then the expected value of a certain function of y, it's the same. It's the integration from negative infinity to infinity. Instead of integrating y, we will integrate g of y, and don't forget to multiply times the PDF itself, f of y dy. Okay? As a special case, let's take g of y as the function y minus mu square, okay, where mu is the expected value of y. Do you remember? This is the variance of y. But then, the variance of y, which is sigma square y, it's the expected value of y minus mu square. How can we get it? We can get it by integration from negative infinity to infinity of this function, which is y minus mu all square times f of y. Or for simplification, we can write it as the expected value of y square minus mu square. And in standard deviation itself is defined to be sigma y, the square root of variance of y. The properties of expectation and variance in the case of continuous variables are the same as the properties in the case of discrete random variables. And here, for a constant c and g1 of y, g2 of y till gk of y be functions of the continuous random variable y. Then, what's the expected value of a constant c? Yes, it's c itself. What's the expected value of c times a certain function g of y? Let's move c to be outside the expectation. or write it as C expected value of G of Y. If we have another functions or different functions, G1, G2 till Gk, but then what's the expected value of G1 plus G2 till Gk? It's the expected value of each one of them. Expected value of G1 of Y plus, let's add the expected value of G2, let's add the expected value of G3, and so on. For A and B are constants. What's the variance of a constant? What's the variance of B? It's 0, yes. The variance of a constant multiplied by the random variable itself. Let's move a constant outside the variance and square it. Okay? The variance of AY, it's A square variance Y. But then when I ask you to find the variance of AY plus or minus B, it will be the variance of AY plus the variance or negative the variance of B. The variance of B itself is 0. And what about the variance of AY? It's A square variance Y. Expectation and variance, let's take some examples. Example number 1. Let y be a continuous random variable with the probability distribution function given by this form: f of y equals cy squared times 1 minus y, and y from 0 to 1. Find the value of c, find the expected value of y and variance of y, and then find the expected value of x. What's x? It's 2y plus 3, and also find the variance of x. A solution. Now, as you know, to find the constant c, we should integrate from negative infinity to infinity of the PDF f of y dy and equate it with 1 and solve this equation. Okay? Like here for our example, we have y from 0 to 1. Let's integrate from 0 to 1. C y squared 1 minus y dy. Okay, let's multiply y squared times 1 minus y. But then we will have y squared minus y cubed. Okay, inside the integration. Then the value of the integration equals c. And what's the integration of y squared? It's y cubed over 3. And what's the integration of y cubed? It's y to the power 4 over 4. Let's substitute from 0 to 1. When we substitute by 1, then we will have 1 over 3 minus 1 over 4, which is 1 over 12. C times 1 over 12 equal 1. Then the value of C is 12. Okay? Now, how can we find the expected value of y? Let's integrate from negative infinity to infinity, y, f of y, dy. Okay? But then let's integrate from 0 to 1 for our example, 12, and let's multiply y times f of y. But then I will get y cubed times 1 minus y. Again, multiply y cubed times this bracket, but then I will have 12. 12 will be outside the integration. Y cubed minus y to the power 4. The integration of y cubed is y to the power 4 over 4, and the integration of y to the power 5 of y to the power 4 is y to the power 5 over 5. Okay? Let's substitute 0 and 1, but then I will have 1 out of 4 minus 1 out of 5, okay, which is 1 over 20 times 12, but then the expected value of y equal 3 out of 5. Let's complete this example. Number 2, to find the variance of y, we should find the expected value of y squared first. How can we find the expected value of y squared? it's equivalent to the integration from negative infinity to infinity y square f of y dy, which is given by, in this example, the integration from 0 to 1, the function itself, okay, PDF, times y square. Here we have 12, and let's multiply y square times the PDF. If we multiply y square times y square times 1 minus y, but then you will get y to the power 4, 1 minus y, okay? Or y to the power 4 minus y to the power 5. What's the integration of y to the power 4? It's y to the power 5 divided over 5. And how can we integrate y to the power 5? It's y to the power 6 divided over 6. Okay, and then substitute. We will have 12 times 1 over 30, which is 2 over 5. Okay, but then the variance equal the expected value of y square, which is 2 over 5, minus mu square. We got mu before, which is 3 over 5, the 3 over 5 square, which is 9 over 25. Okay, but then the variance equal 1 over 25. Now, how can we find the expected value of x? X is a function of y. We have two different ways. We can get the expected value of x mathematically because it's a function of y. Here we have x equal 2y plus 3. But then the expected value of x equal to 2 is a constant times the expected value of y plus 3. The expected value of y itself was 3 over 5, but 2 times 3 over 5, which is 6 over 5 plus 3. Okay? Similarly, how can we get the variance of x? Because x equal 2y plus 3, forget 3, okay? And the constant 2 will be squared. The variance x equal 4 times the variance of y, okay? But 4 over 25. This is the first method. The second method is to integrate, to find the expected value of x, is to integrate from 0 to 1 the function itself, 2y plus 3 times the PDF, y square times 1 minus y times 12, okay? And find the value of this integration. And similarly, to find the variance of y, then we should find first the expected value of x square. How can we find the expected value of x square? X square is 2y plus 3 square. Let's multiply this function 2y plus 3 square times PDF 12 times y square times 1 minus y dy. It seems to be complicated, but let's find, I assume that you will use this method, the first method, because it's a simple, okay? But if anyone uses the second method, it's okay. We have no problem. Let's take another example. Example number 2. The proportion of time y that an industrial robot is in operating during a 40-hour week. Okay? It's a random variable with probability density function given by f of y equal to y from 0 to 1. Find the mean and the variance of the proportion of time that the robot is in operation, yani the mean and the variance of y. For the robot understudy, the profit for a week is given by Lx, it's a function of y, equal 200y minus 60. Find the expected value and the variance of y. Now, the expected value of y itself is given by the integration from 0 to 1 y times f of y. Okay, يبقى expected value of y, here we will integrate y itself times f of y dy. Okay, طيب يبقى it's equivalent to الانتجريشن of y square equal a y cubed divided over 3. Okay, and substitute from 0 to 1, يبقى then expected value of y equal 2 out of 3. How can we find the expected value of y square? Expected value of y square, let's integrate from 0 to 1. Again, let's integrate y square times f of y dy. Okay, يبقى then let's integrate from 0 to 1. 2 times y cubed dy. What's the integration of y cubed? It's y to the power 4 over 4. Substitute, but then we will have 2 out of 4 or 1 out of 2. How can we find the variance of y? It's the expected value of y square minus mu square. 1 over 2 minus 2 out of 3 square. طيب. What about x? X, it's a function of y. How can we find the expected value of a function of y? The expected value of x equal 200 times the expected of y. Expected of y, let's substitute. Okay, here it's 200 times the expected value of y. It's y capital. Okay. It's 200 times the expected value of y, which is a 2 over 3 minus 60. Type. After substitution, the expected value of the profit equal 220 over 3. How can we find the variance of x? Here to find the variance of x, look, here we have 200y minus 60. Forget the minus 60, and 200, this constant will be squared. Even now I will have a 200 squared, which is a 40,000 times the variance of y, which is a 1 out of 18. Okay. Let's take exercises. The first one, the total amount of medical claims in 100,000 of the employees of a company has the PDF given by. You should take care of the unit of measurement. Here we measure in $100,000. Okay. Then when I say that in the PDF f of y equal this form and y from 0 to 1, 1 is the $100,000. Okay. Find the mean and the standard deviation. Look here, I have f of y equal 12y times 1 minus y square. We should expand the bracket. Okay, it's better to expand the bracket first. Okay, or you can integrate by parts if you like it. طيب let's expand this bracket. يبقى here I can say that in the f of y equal ال 12y times this square, this bracket square. Let's square the first term, which is 1, and then square the second term, which is negative 1. Negative 1 square, it will be plus y square. Okay, and then let's multiply 2 times the first term times the second term. 2 times y times 1. Okay, and 2 times 1 times y, and here the sign will be negative. But then I will have, okay, or this is equivalent to 12y minus 24 y square plus 12 y cubed. Or you can take 12 as a common factor. Okay, but then you will have y minus 2y squared plus y cubed. But to find the expected value, let's integrate from 0 to 1. Y times this f of y. Okay, and the standard deviation, as you know, it's the square root of the variance, and to find the variance you should find the expected value of y squared minus L mu squared. Number 2, the probability that the total claims exceeds $20,000. Okay, remember we measure in $100,000. But then $20,000 is less than $100,000. يبقى $100,000 is 1 here, or this is the upper limit. Okay, this is the maximum value that I can reach. يبقى to find the probability that it will, in a random variable, will exceed the $20,000, يبقى then it will be greater than, let's divide $20,000 over $100,000, okay? Because the maximum value is $100,000. يبقى $20,000 represents 0.2 from this one, okay? 100,000 equal 1, or represents 1. يبقى 20,000 represents what? Represents 0.2. You can find it again using by division. Let's divide $20,000 over $100,000. يبقى then you will find that and the value equal 0.2. يبقى let's integrate, exceeds 0.2. يبقى let's integrate from 0.2 till 1. Integrate what? Integrate the PDF itself. Okay. Question number 2, weekly CPU time. Okay, time measured in week. used by an accounting firm has the PDF in hours given by this form. Okay, f of y equal 3 out of 64 y squared times 4 minus y, or y from 0 to 4. Find the expected value and the variance of the weekly CPU time, expected value of y, and the variance of y. The CPU time costs the firm $20 per hour. Okay, but then find the expected value and the variance. But then we will multiply 20 times y, and then I will find the expected value of x, for example, or the expected value of 20y. In this case, it will be 20 times the expected value of y. And what about the variance? The variance, it will be the 20 squared times the variance of y. And here are the answers to check. The moments. Let's define the moments. As you know, we have two different types of the moments, non-central moments and central moments. Let's begin with non-central moments. For a continuous random variable, y, with PDF f of y, the rth moment, r may be 1, 2, 3, 4, and so on. The rth moment of y around the origin, non-central moment, it means that I will find the moment around the origin. Okay, that's why it's defined to be non-central. Here it's given by mu dash r, it's the expected value of y to the power r, and it's equivalent to the integration from negative infinity to infinity, the function itself y to the power r times PDF f of y dy. Okay, it's the same rule as the discrete case, but instead of integration, there we use the sum. Okay, then the non-central moment, it's the same as in the case of discrete random variables. It's the rth moment of the random variable around the origin, and it's given by mu dash r, and it's the expected value of y to the power r. Okay, in the case of discrete random variables, we will take the sum for all possible values of y, sum of y to the power r times the probability mass function of this random variable. But here, for the continuous case, we integrate from negative infinity to infinity, and this is the general upper limit and lower limit, but let's use the upper limit and the lower limit of the random variable given. Okay, but here, because it's a rule, we will write the general case from negative infinity to infinity. Integrate what? Integrate y to the power r, okay? And don't forget to multiply times PDF, okay? dy. For example, mu dash 0, it's the expected value of y to the power 0, which is 1, okay? And mu dash 1, it's the expected value of y itself, and which is defined to be mu. What about the mu dash 2? Mu dash 2, it's the expected value of y square, okay? And because you know that in the variance of y equal the expected value of y square minus mu square, then the expected value of y square equal the variance of y plus mu square. The central moments, the rth moment of y around the mean, okay? And this is the difference between the central moment and the non-central moment. In non-central, it's the earth moment around the origin. But here, the central moment, it's the earth moment, but around the mean mu. Mu r, in this case, it's the expected value of y minus mu to the power r, okay? يبقى here, because it's the moment around the mean, يبقى then we will subtract mu. يبقى it's the expected value of y minus mu to the power r. And similarly, in the case of discrete random variables, we take the sum of all values of y. Sum of what? Sum of y minus mu to the power r times the PDF. Okay? The probability mass function, sorry, in the case of discrete random variables. Here, in the case of continuous random variables, let's replace the sum by the integration from negative infinity to infinity, y minus mu to the power r times the PDF, f of y dy. Then, what about the mu node? Mu node is the expected value of y minus mu. The expected value of y itself is mu. يبقى mu minus mu equal 0. What about, this is mu1, I'm sorry, expected value of y minus mu, it is 0. What about the mu node? The mu node, it's the expected value of y minus mu to the power 0, which is 1. mu2, it's the expected value of y minus mu square, which is the variance of y. Let's take some examples. During an 8-hour shift, the proportion of time, y, the y is the proportion of time, that the sheet metal stamping machine is down for maintenance or repairs has PDF given by this form. The PDF is given by f of y equal 2 times 1 minus y, where y takes the values from 0 to 1, or y is greater than or equal 0 and less than or equal 1. The cost measured in hundreds of dollars of this downtime is given by C equal 10 plus 20y plus 4y squared. Okay, it's a function of y. Now the question is to find the mean and the variance of C, not of y. Okay, here it's a function of y. But then to find the expected value of C, then it's expected value of 10, which is 10, plus 20, the expected value of y, plus 4, the expected value of y squared, and so on. How can we find the expected value of y? The expected value of y equal 2 times the integration from 0 to 1 y times 1 minus y dy equal 2 inside the integration we have y minus y square. Okay, the integration of y is y square over 2 and the integration of y square is y cubed y cubed divided over 3. Okay, this is the 3 written by using the mouse. Okay, and then we substitute 0 and 1. Okay, which is a 2 times 1 over 6, which is 1 over 3. It's okay. 3 is okay now. Okay? But this is the expected value of y. Similarly, we can find the expected value of y square. Okay? And then let's substitute. How can we find the variance of c? The variance of c itself is the expected value of c square minus the expected value of c all square. The expected value of c square, it's the expected value of the function itself square. Okay? Then let's expand this bracket. It will be, the 10 square will be 100 and the 20y will be 400y square. And then we have 16y to the power 4. Okay, يبقى here we will square this term, which is 100, and let's square this term, which will be a 400y square, and let's square this term, which will be 16y to the power 4, and then let's take 2 times 10 times 20y, which is 400y. Okay, that's why we got this term. And then 2 times 10 times 4y square, which is 80. Okay, but that's why we got 480, we got it because I have 400 plus 80. Okay? طيب, and then if we multiply ال 20y times 4y square times 2, then I will have 160y cubed. Okay? Again, to expand the bracket, we will have, I will write all the terms here vertically. And then let's add them. I will have 100. Okay? And then I will have 400 y square. And I will have 16 y to the power 4. I got these elements when we square each one of the 3 elements, okay? And then we should add, let's use another color. Let's add 2 times 10 times 20y. Okay? And then 2 times 10 times 4y square. And we multiply the first term times the second term times 2. And then the first term times the third term times 2. And then the second term times the third term. يبقى 2 times 20y times 4y square. Okay? Let's add all these elements. Look, here we have 100. Okay? And then from here we have 400y. Okay? 400y. And then the coefficient of y square, we will add this term 400y square plus this term 80y square. Okay, even then we got 480y square. And then this term 2 times 20, 40 times 4, 160y cubed. This term. Okay, and the last term is 16y to the power 4. And we try to find the expected value of all these terms. Okay, but then we have the expected value of y. Let's substitute with 1 over 3 and the expected value of y square. Similarly, we can find the expected value of y cubed and y to the power 4 using this, okay, using the integration. Yani for example, the expected value of y cubed equal to times the integration from 0 to 1 y cubed times 1 minus y. Then we finished the moments. Let's now talk about the moment generating function. The moment generating function has the same definition as in the case of discrete random variables. Okay, if you remember, a moment generating function was given by, in the case of discrete random variables, my of t, it's the expected value of e to the power ty. Okay, what's the difference? The difference is that here we will use the integration from negative infinity to infinity. Integrate what? Integrate e to the power ty itself. We will assume that it's a function of y times the PDF f of y dy. But in the case of discrete random variables, we have to write the sum, okay, of all possible values of y, e to the power ty times the probability mass function. Okay? Here we will assume that for a certain constant h, my of t exists, okay, such that my of t, the moment generating function, is finite for t that lies in this interval. Sometimes the moment generating function does not exist, okay, and sometimes we can find it. This means that I cannot find the moment generating function for all random variables. And remember, there is a one-to-one correspondence between the PDF and the cumulative distribution function and the moment generating function, which means that for each variable, I have only one PDF and one CDF and one moment generating function. Sometimes for the continuous case, I cannot get the moment generating function for some variables. Okay? Here, the moment generating function, if I took the constant equals 0, it will be the expected value of e to the power 0, which is a 1. Never take the constant equal 0. It should be greater than 0. Generating moments. As you know, this function is defined to be the moment generating function because using this function, I can get the moments, okay? As in the case of discrete random variables. In general, how can we get the earth moment? The earth moment, I can get it by differentiating the moment generating function r times with respect to t, and after finishing the differentiation substitute t equal 0. Okay? But then to find the expected value of y to the power r, or mu dash r, for example, and here, remember, I can get only the non-central moments using the moment generating function. Okay? If I ask you to get central moments, then you can substitute. And you can find non-central moments, and then, for example, if I ask you to find the second central moment, which is the variance, how can we get the variance? Let's differentiate the moment generating function once to get the expected value of y, and second time to get the expected value of y square, and then to find the variance, which is the second central moment, you can subtract the expected value of y square minus the expected value of y all square. Now let's go back to the moment generating function. Here, if you try to find the expected value of y to the power r, or which is mu dash r, then let's differentiate r times the moment generating function with respect to t, and after finishing the differentiation r times, let's substitute t equal 0. Here r equal 1, 2, 3, whatever the value of r. But then, when I ask you to find the first moment, the expected value of y, but then let's differentiate the moment generating function only once, and then substitute t equals 0. Similarly, how can I find the expected value of y square? Let's differentiate it twice, and then equate it with 0. Properties of the moment generating function. If the y is the random variable with moment generating function my of t, and a and b are constants, then the moment generating function of, here we will have another variable. Instead of y, I have y plus a. Okay? In this case, the moment generating function of y plus a, or the expected value, okay? This will be the expected value of e to the power t times y plus a plus y plus a. Of course, writing using mouse is very difficult. Okay, this is why. It's the expected value of e to the power ty, okay, and we can move outside e to the power at, okay. Then it's e to the power at times the moment generating function of y over t. Right. What about the moment generating function of by over t? يعني expected value of e to the power b t y. Let's assume that the constant itself is bt. It's the moment generating function, but instead of over t, it's over bt. And the random variable itself is y. Right. Here, moment generating function of y plus a over b. It's the expected value of e to the power a over b t, because here we will multiply y plus a over b times t. But then I will have y over bt plus a over b times t plus y over b okay, which is equivalent to e to the power a over b t. It's a constant, and here instead of the constant t, the constant in this case will be t over b. Okay, it's very simple, and it's not necessary to memorize these rules. You can find them just by one step. Examples. I have a random variable y with density function e to the power y, and y less than 0. Less than 0, it means that it begins from negative infinity to 0. Find the moment generating function and use it to find the first 3 moments, okay? And then find the variance of y and find the expected value of another function. How can we get a moment generating function? It's the expected value of e to the power ty. And here we will integrate from negative infinity to 0 e to the power ty times the PDF itself. This is our PDF, e to the power y. But then the integration, it will be e, inside the integration I will have e to the power y times t plus 1. And as you know, the integration of e to the power ax, okay, it will be e to the power ax divided over a, where a is a constant. This is in general. What's the differentiation of e to the power y times t plus 1? It will be e to the power y times t plus 1 divided over t plus 1. Okay. Let's substitute from negative infinity to 0. If we substitute y equals 0, it will be 1. If we substitute y equal negative infinity, as you know, e to the power negative infinity equal a 0. But then the moment generating function equal 1 over t plus 1. Right. How can we find the first, second, or third moments? Let's differentiate this function. Okay? Right. And here, because I have 1 over t plus 1, t should be greater than negative 1. Okay? If t equal negative 1, then I have a infinity, which is, of course, I can't have a moment generating function equal infinity. How can we differentiate infinity? Okay? Right. Let's differentiate for the first time, because here we will have t plus 1 to the power negative 1, but its differentiation will be negative 1 times t plus 1 to the power negative 2. Substitute t equals 0, but then the first moment equal -1. Similarly here, let's differentiate this function. Don't differentiate in -1, of course. Differentiate the first derivative again to get a second derivative. يبقى let's differentiate -1, it will be negative, يبقى positive, okay, with t plus 1 over -2, يبقى then I will have 2 times t plus 1 to the power -3. After substituting t equals 0, I will get the expected value of y squared. طيب, again, to find the expected value of y cubed, let's differentiate this function. Okay? طيب, to find the variance of y is the expected value of y square minus the expected value of y all square. طيب, how can we find the moment generating function? Here, the expected value of e to the power 3y over 2. Okay? Which is the same as the moment generating function of 3y over 2. Okay? طيب, using the rules, how can we find the moment generating function of 3y over 2? It will be the moment generating function of y of 3t over 2. يبقى here, let's replace it t by 3t over 2. Another example. I give you the moment generating function in this form. E to the power 3t plus 8t square. Let x equal y over 3 and z equal 2y plus 5. Find the moment generating function of x and z. Okay? Here, the moment generating function of x is the moment generating function of y over 3 of t, which is the same as the moment generating function of a t over 3 of y itself, but over t over 3. Okay? يبقى here, let's replace each t by t over 3. يبقى it will be e to the power 3 t over 3 plus 8t over 3 all square, and simplify. طيب, what about z? Z equal 2y plus 5. It's the moment generating function of 2y plus 5. طيب, يبقى let's take the constant e to the power 5t times the moment generating function of y, but instead of t, let's use 2t. طيب, يبقى let's multiply e to the power 5t times the moment generating function after substituting t by 2t. يبقى e to the power 3 times 2t plus 8 2t square, and then simplify. Exercise: a random variable has the density function given by this form and y from -1 to infinity. Find the moment generating function. How can we find the moment generating function? By finding the expected value of e to the power t y. But then let's integrate from -1 to infinity. E to the power ty times e to the power -y minus 1, and here we will add the powers of t, okay, to find the integration. And then use this moment generating function to find the expected value of y and the variance of y, and then find the cumulative distribution function. How can we find the expected value of y? By differentiating the moment generating function, okay, and then substituting t equals 0. And how can we find the variance of y? By differentiating this function twice, okay, and here we will have numerator and denominator, okay. But then let's use the rule of differentiating when I have a fraction, which is the denominator square and in the numerator I will have the denominator times the numerator, the derivative of the numerator, minus the numerator times the derivative of the denominator. Try to make a revision on the rules of differentiation, please. Use the moment generating function to find the expected value of y, okay, and the variance, and then find capital F of y, cumulative distribution function. Let's integrate from -1 to y, and let's replace y inside the integration to be z, for example. Okay, then I will get the cumulative distribution function in this form. Then we finished the moment generating function. But then we talked about continuous distribution functions, continuous random variables, then their probability density function, their cumulative distribution function, expectation, variance, moments, and the moment generating function. If you have any question, of course, you can ask me by email or ask Rania. Thank you.